A 907-kilogram bomb plummets towards the open waters of the Gulf of Oman. It's not targeting a ship, but an empty patch of ocean, just 9.1 meters off the port side of an Iranian supply vessel attempting to breach a blockade. This bomb isn't interested in the deck, its true target lies beneath. A mere 3 seconds before impact, the seeker in its nose performs an unprecedented maneuver for a gravity bomb. It turns, not towards the steel hull, but precisely towards the waterline. What unfolds in the next 1.4 seconds is why the United States Air Force can now effortlessly break a ship in half without needing a submarine, and at a cost less than a new pickup truck. The United States is currently enforcing a full naval blockade on every Iranian port. Any vessel entering or leaving Iranian waters is subject to interception. This isn't a brief, one-day operation, it's an open-ended siege, sustained until Tehran's economy either collapses or its government agrees to negotiate. This necessitates stopping ships. Vessels that refuse to comply must be disabled. And those that resist must be sunk. Not just once or 10 times, but every day, every week, for as long as the mission demands. Yet, there's a critical problem no one is discussing: sinking a ship is incredibly expensive. A Mark 48 heavyweight torpedo costs $4 million. A long-range anti-ship missile, like the LRASM, comes in at $3.24 million. Contrast this with the average Iranian supply vessel attempting to breach the blockade, which is often worth less than $500,000. Imagine spending $4 million to sink a $500,000 ship, 5 times a week. In just 1 month, you'd expend $65 million in ammunition alone on targets collectively worth less than $10 million. This unsustainable ratio doesn't maintain a blockade, it bankrupts it. The United States Air Force, however, has solved this dilemma. Not with a new missile or a submarine, but with a 907-kilogram bomb, already stockpiled by the tens of thousands in warehouses, now modified with a seeker that costs less than a mid-range sedan. This ingenious solution, how it works, why it works, and what it signifies for the 2 aircraft now enforcing the blockade from the sky, is precisely what we'll explore on Global Chessboard. This episode fundamentally changes the calculus of naval warfare. But before diving into this groundbreaking solution, it's crucial to understand why traditional methods of sinking ships were destined to fail at Hormuz. The answer isn't about technology, it's about water itself. For the past 4 decades, every weapon the United States employed to sink enemy vessels was designed for a different kind of conflict. Torpedoes were engineered for deep-water engagements against formidable Soviet submarines. Anti-ship missiles were built to neutralize heavily defended warships equipped with radar and sophisticated countermeasures. These are precision instruments, crafted for high-value targets. A blockade, however, isn't a high-value target problem, it's a volume problem. Dozens of vessels, cargo ships, tankers, even fishing boats repurposed as supply runners, attempt to cross the line every single week. The vast majority are worth less than the weapon required to stop them, making traditional options economically unfeasible. Consider a Virginia-class submarine, carrying approximately 25 torpedoes. At $4 million each, that's $100 million worth of ammunition housed within a $3.4 billion hull. To reload, the submarine must return to port, a round trip that can take weeks. Furthermore, operating a submarine in the shallow, mine-seeded waters near Hormuz presents a calculated risk that no fleet commander would undertake lightly. The missile alternative offers no improvement. The LRASM, designed to defeat warships protected by advanced radar and close-in weapon systems, is grossly overqualified for the task. Using it on an unarmed cargo vessel is akin to dispatching a Formula One car to deliver groceries. It works, but the economics are utterly obscene. The blockade desperately needed a weapon that was cheap, accurate, and lethal enough to sink a ship in a single pass. Such a weapon didn't exist 5 years ago. But it does now. The physics behind it begins with a question most people answer incorrectly: what actually sinks a ship? The answer isn't fire, nor is it merely a hole in the hull. It's something far more violent: and it happens underneath. Imagine dropping a 907 kilogram bomb onto the deck of a cargo ship. The bomb would punch through the steel plate, detonate inside the superstructure, transforming the upper decks into an inferno. The crew would be incapacitated, the bridge obliterated, and fire would rage through every compartment above the waterline. Yet, despite the devastation, the ship would still be floating. Below the waterline, the hull would remain intact. Watertight compartments would be sealed, and the structural keel, the backbone running the entire length of the ship, would be undamaged. A large vessel can endure 2 or 3 direct hits to its deck and still drift for hours, sometimes even days, before slow flooding finally claims it. This is the fundamental physics that Hollywood consistently misunderstands. Explosions above the waterline destroy equipment and kill crews, but they do not sink ships. To sink a ship reliably, quickly, and with a single weapon, you must attack it from below. This is precisely what a torpedo achieves. A Mark 48 doesn't strike the hull from the side, it detonates directly underneath the keel. Water is incompressible. When the warhead explodes beneath the vessel, the shockwave doesn't dissipate outwards as it would in air. Instead, it transmits entirely upwards, directly into the bottom of the hull. 3 sequential events unfold. First, the shockwave violently lifts the ship's midsection out of the water. Second, the expanding gas bubble creates a void, a cavity of nothingness, directly beneath the keel. Third, the bubble collapses, causing the ship's midsection to plummet into that void. With the bow and stern still supported by water, the ship's own immense weight, tens of thousands of tons, does the rest. The keel snaps. The ship breaks in half. The same explosive force creates a fire above deck, but below the keel, it creates a broken spine. Position is everything. And this, frankly, is why torpedoes are so exorbitantly expensive. Engineering a weapon capable of navigating to the precise spot underneath a moving ship, at the correct depth and angle, represents a $4 million problem. The Air Force, however, posed a different question: what if the weapon didn't have to swim? What if it could simply fall? The answer to that question has a name, and it's already operational: QuickSync. QuickSync isn't a new bomb, it's an old bomb with new eyes. It begins with a GBU-31 Joint Direct Attack Munition, a 907 kilogram gravity bomb guided by GPS and inertial navigation. The Air Force possesses tens of thousands of these in inventory. The kit alone costs roughly $25,000 and has been the backbone of precision strike since the late 1990s. Now, imagine bolting a seeker onto its nose. Not a radar seeker, nor a laser designator, but a multimode sensor built on the Weapon Open Systems Architecture, or WOSA, a modular, plug-and-play framework that accepts targeting components from various manufacturers. This seeker autonomously detects, classifies, and tracks surface vessels. The target cost for this seeker, at serial production, is $50,000. The total system cost, at production scale, is approximately $70,000, the Air Force's objective unit price once the seeker line reaches high volume. Compared to a $4 million torpedo, this represents an astonishing ratio of 1 to 57. Here's how it works in practice. The bomb is released from the aircraft, an F-15E Strike Eagle, a B-2 Spirit, or any platform cleared to carry dams. GPS guides it precisely to the target area. As it descends, the WOSA seeker activates, locks onto the ship, and calculates an impact point not on the deck, but at the waterline, immediately adjacent to the hull. In its terminal phase, the bomb executes a sharp trajectory correction, punching directly through the surface of the water beside the ship's keel. The nose cone has been specifically redesigned to prevent skipping. At high velocity, water behaves much like concrete. A conventional bomb striking the surface at a shallow angle would ricochet and miss. QuickSync's nose geometry ensures deep penetration. The bomb enters the water, positions itself beneath the hull, and detonates. From that moment, the physics are identical to a torpedo: shockwave, bubble, collapse, keel break. The ship simply doesn't know the difference. QuickSync doesn't build a new bomb, it gives an old bomb a profound diving lesson. The same 907 kilogram warhead the Air Force has been deploying from Strike Eagles for 3 decades has now been taught to swim. And this isn't merely theoretical. In 2022, an F-15E from the 53rd Test and Evaluation Wing successfully deployed a QuickSync weapon in the Gulf of Mexico. The target vessel, a full-scale, real steel ship, broke apart and sank within minutes. Then, in July 2024, during the RIMPAC exercise, a B-2 Spirit employed QuickSync against the ex-USS Tarawa, a 40,000-ton amphibious assault ship, measuring 250 meters long. The weapon performed flawlessly. The ship went down. The physics are proven. The cost problem is solved. The next crucial question is who delivers this weapon, and how 2 vastly different aircraft divide the responsibilities of a blockade. This bomb has eyes, but it still requires a sophisticated kill chain, a chain with 4 critical links, 2 that watch, and 2 that strike. A bomb capable of sinking a ship is useless without precise coordinates. QuickSync needs to know the target's exact location, its speed, and where to aim. This vital information originates from 2 platforms the target ship will never detect. High above the Gulf, the E-7 Wedgetail continuously scans the ocean. Its MESA radar, an active electronically scanned array mounted on the back of a Boeing 737, doesn't rotate mechanically like the old E-3 Sentry's dish, it steers its beam electronically. While the E-3 completes a full scan every 10 seconds, the E-7 can update a sector of interest in just 3. A fast attack craft speeding at 92.6 km per hour covers less than 80 meters in those 3 seconds, meaning the Wedgetail never loses track. Operating lower and slower, the MQ-9B Sea Guardian fills the gaps the radar cannot. With over 30 hours of continuous flight, its electro-optical and infrared sensors can read hull markings from high altitude. It doesn't just find targets, it confirms them, verifying whether a vessel is carrying concealed weapons, military cargo, or an IRGC boarding crew. The Wedgetail sees everything, the Sea Guardian identifies what truly matters. Both feed their data into the Joint All-Domain Command and Control Network, or JADC2. This advanced battle management system processes the feed, calculates precise targeting solutions, and pushes coordinates directly into the cockpit of the strike aircraft. The delay between detection and weapons release is now measured in seconds, not minutes. Now, for the strike. The blockade effectively divides the ocean into 2 distinct zones, each assigned to a different aircraft. The F-15E Strike Eagle dominates the open water, the Gulf of Oman, safely beyond the reach of Iran's coastal air defenses. The Strike Eagle carries 4 or more QuickSync weapons per sortie, orbiting visibly above the shipping lanes. The A-10 Warthog previously demonstrated that a low-altitude presence and Channel 16 warnings can often persuade a tanker to turn around before any weapon is released. The F-15E inherits this crucial escalation ladder. But when warnings fail and a vessel continues its course, the Strike Eagle carries what the Warthog does not, it receives coordinates from JADC2 and delivers a weapon that decisively ends the argument below the waterline. The ship's captain sees the fighter overhead, loaded, circling, patient, that is the ultimate message. If that message fails, the bomb does not. Meanwhile, the B-2 Spirit owns the coastline. Near Bandar Abbas, deep within the engagement envelopes of Iran's Bavar 373 and S-300 surface-to-air missile batteries, no conventional fighter could survive. The B-2, however, doesn't need to survive detection, it avoids it entirely. Its stealth geometry carries it through radar coverage completely unannounced. It targets supply vessels sheltering near port, vessels that mistakenly believe proximity to shore-based air defenses makes them safe, and delivers QuickSync from directly above. Iran sees no aircraft on radar, hears no engine noise. The ship simply breaks apart and sinks. One visible, one invisible, both carrying the same $70,000 weapon. The F-15E enforces through presence, while the B two enforces through absence. Together, they leave no gap in the blockade line. There is, however, a technical limitation worth noting. QuickSync possesses no electronic countermeasure suppression capability. Against an Iranian frigate employing active radar and a close-in weapon system like the Kaman, the bomb would be vulnerable during its terminal descent. This is precisely where the LRASM earns its substantial price tag. It suppresses the ship's defenses from a standoff range, effectively clearing the airspace for QuickSync to finish the job uncontested. The expensive weapon blinds the target, while the cheap weapon breaks its spine. So, what does all of this truly mean? Every piece of what you've just witnessed addresses a singular part of the blockade equation: why traditional weapons lead to mission bankruptcy, why bombs must detonate below the waterline, not above, how a $50,000 seeker transforms a standard warehouse bomb into a guided torpedo, and how two aircraft, one loud, one silent, divide the ocean between them. But there's a larger question that none of these individual answers can fully address. If the Air Force can now sink ships with gravity bombs and a data link, what purpose does the submarine still serve? The answer reveals the true insight: QuickSync doesn't replace the submarine, it liberates it. Before this weapon existed, a Virginia-class attack submarine was tasked with doing everything: hunting surface vessels, tracking Iranian Kilo-class submarines hiding below the thermocline at 61 meters, collecting intelligence, and launching Tomahawk strikes against land targets. For critical missions, with a mixed magazine of torpedoes and cruise missiles shared across every target type on the priority list. One hull, with no capacity to spare. QuickSync completely strips away the first mission. The Air Force now owns the surface. The F-15E clears the open water, and the B-2 clears the coast. The submarine, now freed from surface interdiction, can pull back to the thermal layer and refocus its efforts. While Iran's Kilo-class boats were neutralized in the opening days of Epic Fury, the submarine threat doesn't end with 3 holes on the seabed. Acoustic intelligence collected in the 72 hours after the blockade began has already detected signatures that do not belong to any known Iranian platform. Someone else is watching, and tracking what's down there without being detected is a mission only one platform in the world can execute. That platform is now free to focus on nothing else. The Air Force takes the surface, the Navy takes the depths. The blockade now has no seam. And observe the profound irony. Water, the antagonist throughout this entire discussion, the very substance that makes bombs skip, shields hulls, and transforms shockwaves into complex physics problems, is precisely the reason QuickSync works. Water is incompressible. That property is why it defeats conventional deck strikes. And that exact same property, incompressibility, is what transmits 100% of the shockwave directly into the keel. The enemy has, in essence, become the weapon. Most people will watch the news and simply see a ship sink. But you now understand the intricate physics beneath it: the shockwave, the bubble, the $70,000 equation that has replaced a $4 million torpedo. If appreciating that distinction matters to you, let us know by typing "proud" in the comments, proud not of the weapon itself, but proud that you comprehend the ingenious engineering behind it. Join us on Global Chessboard as we continue to build that understanding, one episode at a time. QuickSync has unequivocally proven that a $70,000 bomb dropped from a stealth bomber can accomplish the mission of a $4 million torpedo launched from a $3 billion submarine. The physics are settled. The tests are complete. The blockade is actively employing them. The real question is not about the weapon itself, it's about what this signifies for everyone else watching. If the Air Force can now sink entire fleets with cheap gravity bombs and a sophisticated data link, what does that mean for every Navy worldwide that built its entire doctrine around the assumption that sinking ships demands expensive missiles and costly platforms? That fundamental assumption just hit the water, and it decidedly did not float.